Let's work an example work problem. Determine the amount of work each force does on a 10-kilogram block pulled 8 meters along the flat ground by a 50-newton force applied to a rope that is angled 60 degrees above horizontal. The coefficient of kinetic friction is 0.2. So I'm going to go ahead and label all my forces first so I don't forget any when I'm trying to figure out which one does work. I'm going to call this FA for the applied force, and it is equal to 50 newtons, and it is applied 60 degrees above horizontal. 60 degrees. Now the block is actually moving to the right, and it moves 8 meters. And let's see, there is the force due to gravity, Fg. There is the normal force, Fn. And of course there is the frictional force, Fk. We're supposed to figure out how much work each one of them does. Well, let's start with the easy ones. This thing is moving to the right. Fn is not doing any work, so the work of Fn is equal to 0. The work of Fg is also equal to 0. And the reason I can say that, work equals force times distance times the cosine of the angle between them. These are at right angles, and the cosine of 90 degrees is equal to 0. So since the force and the motion are at right angles for the normal force and gravity, those two forces do no work. But when we come to the force of the rope, or the Fa, does it do work? Well, some of it does, because what I have is a distance of 8 meters, right? Work equals force times distance times the cosine between them. So I have a distance of 8 meters, a force of 50 newtons, and an angle of 60 degrees, and since the motion is to the right and the force is up and right, that's the angle I want. So I have 50 times 8 times the cosine of 60. And if we work out that math real quick, 50 times 8 times the cosine of 60, we get 200 joules. So the green force, the applied force, does 200 joules of work. The only other force left to investigate is the frictional force. How much work does it do? Well, we actually need to know how big that force is. But remember, the kinetic frictional force is equal to the coefficient of kinetic friction times the normal force. Now, be sure you're looking at your picture. A lot of times we just like to say that the normal force is equal to Fg. In this case, we can't do that because this force, Fa, has a component in the y direction. So the net force in y is equal to the normal force plus the applied force in the y direction minus Fg, and that is equal to 0. So if I can find those two forces, I'll know Fn. Fn equals Fg minus Fay, which is equal to mass, 10, times the acceleration due to gravity, 9.8, minus the applied force in the y direction, which is just those 50 newtons of force times the sine of the angle, 60. So 98 minus 50 sine 60 is 54.7 newtons. Use that over here, times the coefficient of friction, 0.2, times 54.7, and I get that the kinetic frictional force is equal to 10.94 newtons. Okay? So kinetic friction, 10.94 newtons. How much work does it do? Well, the work from kinetic friction is equal to 10.94 times the 8 meters that the object moves times the cosine of 180 degrees. So times 8 times -1 times 10.94, that gets me negative 87.52 joules of work. It is negative because the force and the motion are in opposite directions. It's moving to the right, friction is to the left. Now I want you to think about this for a minute. The applied force did 200 joules of work, and the frictional force did negative 87.52 joules of work, which gets me a total work of 112.48 joules. If we think about that for just a little bit, we understand that the applied force is doing a heck of a lot more work than the friction, and that means that this box is probably getting faster. The other way we can think about that is in terms of balanced and unbalanced forces, but since more work is done to put it in motion than to oppose the motion, it does make sense that the work is getting, or that the velocity is increasing.